On March 22, 2026, Air Canada Express Flight 8646 was on final approach to LaGuardia Airport when it suffered a devastating collision with a fire truck, which tragically claimed the lives of both pilots and also left several passengers seriously injured. This accident was one of the most severe to occur at LaGuardia in recent decades, and the first with fatalities in more than 30 years. But to understand the key factors behind this air disaster, we conducted a full technical analysis to reconstruct the sequence of events and determine the causes that ultimately led to the accident. Air Canada Express Flight 8646, operated with a Bombardier CRJ-900, was in the final stage of approach to runway 4 at LaGuardia Airport. The aircraft was flying a stabilized descent profile with a standard landing configuration. Landing gear down, flaps extended, and speed gradually reduced toward approximately 130 knots. At that moment, the operational environment was far from routine, as traffic had built up due to delays caused by adverse weather conditions, with rainfall reducing visibility, and a wet runway increasing overall stopping distance for the aircraft. As the aircraft crossed the runway threshold and entered the final landing phase, its kinetic energy remained extremely high. Even after touchdown, a jet like the CRJ-900 still retained significant inertia that had to be dissipated through aerodynamic braking, reverse thrust, and wheel braking systems during the landing roll. At the same time on the ground, a second chain of events was unfolding. An aircraft rescue and firefighting vehicle, a high-mass airport fire truck, had been cleared to cross the active runway to respond to another emergency situation. This type of vehicle can easily weigh over 40,000 pounds when fully equipped with firefighting systems, meaning its acceleration and maneuverability are limited, especially in low traction conditions and on wet runway surfaces. The aircraft continued along the runway at an estimated speed of around 90 knots, equivalent to approximately 104 miles per hour. At that speed, stopping distance is not immediate, and the aircraft requires several thousand feet to fully dissipate its energy. During the first few seconds after touchdown, the aircraft's lateral control was very limited, and although it had rudder authority and nose-wheel steering, their effectiveness largely depended on speed and runway conditions. However, on a wet runway, the coefficient of friction is significantly reduced, limiting both braking performance and overall directional control. Within that same time window, the fire truck began crossing that section. Its movement was perpendicular to the runway axis, meaning both vehicles were on a collision course. Here appears a critical factor, known as temporal perception. From the aircraft cockpit, forward visibility is conditioned by several elements: the descent angle, the cockpit height relative to the ground, and the possible presence of rain or fog. All these elements can significantly delay the visual detection of an obstacle on the runway in all cases. When the aircraft was already in landing protocol, the crew's main attention was focused on deceleration, directional control, and system monitoring. Therefore, reacting to unexpected obstacles at short distance was almost impossible indeed. For his part, the truck driver was also facing several limitations. His visibility may have been affected by the elevated cabin, nighttime lighting, and weather conditions. In addition, the acceleration of this type of vehicle does not allow the runway to be cleared quickly once the crossing has begun in use. At that moment, the air traffic controller issued a stop command for the truck. However, that order unfortunately arrived too late to act. The collision occurred under a highly unfavorable configuration for the aircraft, as the impact was almost entirely frontal and also against a rigid object of enormous mass. From a structural point of view, the nose of the CRJ-900 is an area primarily designed to house avionics and provide improved aerodynamics, not to absorb high-energy impacts against massive objects at all times. The result was an extremely abrupt deceleration concentrated at the front. The aircraft's kinetic energy could not be dissipated progressively, transforming almost instantaneously into structural deformation. The dominant physical phenomenon in this type of impact is violent deceleration. The aircraft went from tens of meters per second to nearly zero over an extremely short distance. This generated enormous inertial forces, which were transmitted directly to the aircraft structure and its occupants. The cockpit absorbed most of the impact. The pilots located in that area received the maximum energy load, which explains the total destruction of that section and the tragic death of Captain Antoine Forrest and First Officer Mackenzie Gunther in that event. After the initial impact, the aircraft structure experienced a progressive breakup. The forward section was destroyed and the remaining energy was transmitted into the fuselage, generating additional deformations. The deceleration of the rest of the aircraft continued for a few seconds, but in a less abrupt and violent manner, allowing most of the passengers to survive, although with injuries of varying severity. The truck, for its part, also experienced a massive transfer of energy. The difference in mass and the geometry of the impact determined the aircraft's effect. The enormous mass of the moving aircraft collided with the vehicle structure, producing severe deformations in the truck. Fortunately, both occupants survived the impact, but they suffered fractures and other significant injuries as a result of the collision. Regarding the causes that led to the accident, a key aspect in the sequence of events was the absence of an effective prior warning. The surface surveillance system did not generate an alert because the truck was not equipped with a transponder, which reduced the system's ability to identify it accurately in time. This meant that in the absence of automatic alerts, safety depended largely on the situational awareness of the air traffic controller, who at that moment was also managing multiple events simultaneously at once. In this context, there is another fundamental element that often goes unnoticed, but is important to consider: fatigue during night shifts in general. Air traffic control is an activity carried out 24 hours a day, but during the night staffing levels are usually lower, while workload can increase at specific moments in abnormal situations, as unfortunately happened that fateful night in question. Various studies by the Federal Aviation Administration indicate that rotating and night shifts disrupt circadian rhythms, reduce concentration capacity, and lengthen reaction times, especially when they coincide with high-demand scenarios or multiple incidents occurring simultaneously in real operational environments. The CRJ 900 accident at LaGuardia clearly shows how the combination of reduced visibility, failures in alert systems, and various human factors and errors can quickly lead to extremely serious accidents. And with this, we reach the end of today's video. If you enjoy our work and want to support us, we would greatly appreciate it if you subscribed and left us a like. So besides helping us keep creating content, you will also stay fully up to date with all the new uploads on the channel. Finally, before to sign off, we would like to hear your opinion in the comments, and know who you think was truly responsible for this tragic accident. Thank you all very much for supporting the channel. I read your comments, and we'll see you in the next video.